the GD&T Guy, and you are on video 7 of a deep dive into a somewhat niche topic in the world of mechanical design, engineering drawings, and geometric dimensioning and tolerancing, GD&T for short. If you like this video, please like and subscribe so you get the rest of them in your feed. Also, comment with your agreements and disagreements. Help me identify any mistakes I've made. And in the video descriptions, I will post a link to where you can find PDFs of all the drawings I discuss so you can pause and look at them yourself. Okay, let's go. For the previous videos, I've been talking about this very popular way to locate parts using dowel pins. This has led me into some of the nitty-gritty details of mechanical design, machined parts, and the tolerances we apply on engineering drawings. I told you way back in video 1 that this interface has a lot going for it and there's a reason for its popularity. But I also said that it is highly reliant on tight machining tolerances to produce a highly repeatable fit. And I tried to show that there are some problems this interface cannot solve. My argument is, just like everything in engineering, we should take a judicious approach. If this interface is justified, then go ahead and use it. But I will say, I think it's overused in industry. My guess is that most engineers learn about this way of using dowel pins early in their career. They recognize its elegance and they start using it everywhere. So what's the downside? Well, the extra process step of installing the pins and the close tolerance features definitely add expense. And maybe that expense doesn't bother you, but if you pay and then the parts still won't fit together on the pins, or if they get stuck, that's pretty frustrating. I've tried to show you how to size features and to apply tolerances so these bad things won't happen. But if you're trying for a super close fit, it's still possible, and it can be hard to figure out where the mistake was made. And even if you find out who is responsible, it doesn't change the fact that you're losing time with your parts and rework when you need to be building. But I would say there's an even bigger problem, which only the experienced seem to think about. This stems from the fact that the pinned interface is pinned. That is, it can't move. A lot of times with our bolted assemblies, it can really help in putting things together to lightly tighten the screws, shift the parts around a little bit within the screw clearance holes, and then when all the parts are well aligned, we come in and we tighten all the screws. You don't get that with the pins. The parts locate where the pins put them. If a part is in the wrong position, there's nothing you can do to shift it around, unless you pull out the pins to free it up. So with the next 2 videos, I want to provide a few ideas that just might solve some of these problems. And we'll talk about their pros and cons as well. Could be fun. Have a look at this assembly, which looks pretty similar, except the blue part now locates on a hole in a hole instead of a hole in a slot. Now we said we liked that slot because it prevents the interface from being over-constrained. If there is any difference between the pin-to-pin distance on this part and the hole-to-hole distance in this part, we have a problem, right? Well, only to the extent that the holes are close fitting on the pins. You know and I know that if we make these holes large enough, we can get them to fit over the pins. And if you've been watching this series so far, maybe you can guess that it's all going to be about matching the virtual conditions of both parts. So let's go into this drawing of the gray part with the pins. This is GD&T 00409. Now there's a lot to this drawing that's very similar to what we saw in video 6 with GD&T 00401, so I won't repeat all that. But in case you're starting with this video for some reason, the one strange thing about this drawing that I must point out is that it only depicts a detail area of a larger part that we just have to imagine. Just like in GD&T 00401, I call this flat surface my datum M feature. And then when it comes to the call out for the 2X dowel pins, we start off similar and then we go in a different direction. I still have 2 frames of position control, one in the ABC datum reference frame, which locates these pins within our larger imaginary part. And then the second frame controls these pins as a pattern, related only to datum M primary. Effectively, this is where we control the distance between the pins. And following the method we've established now over all these videos, we have our 4/1000ths of position tolerance plus the 0.2503 mmc of the pins, add those together, and we end up with a virtual condition, VC, of 0.2543. A lot like in GD&T Guy 00401, this could be verified with a gauge of extraordinary geometric accuracy. This gauge would have holes corresponding to the pins, sized at that virtual condition, 0.2543 diameter, perfectly perpendicular to our datum M simulator here, the flat surface, and exactly the right distance apart. And the gauge would have to fit down over the pins of our manufactured part. Let's look straight down on it here so you can see the very small amount of position tolerance. Back to drawing GD&T Guy 00409. One difference between this one and 401 is that I had included in the stack of callouts a perpendicularity of the individual pins to datum M. I'm skipping that here. I'm going to let the second frame position tolerance also control our perpendicularity. The pins will still have to be in those virtual condition size holes. Get it? And here's something new and special and different. I attached a datum feature symbol to this callout for the 2x pins. With this, what we're saying is that we have a datum pattern of features. And you can see in the callout for the threaded holes that I use this as a secondary datum with no tertiary datum. Really what we have here is a 3 degree of freedom primary datum and a 3 degree of freedom secondary datum. This is totally legit, and actually there's something I really like about it. It dispenses with that semi-fiction that one of these pins is more special than the other in locating the part. I think there's a great argument that the XYZ origin of this interface is no longer at that point where the axis of one of the pins meets datum M. With this, the XYZ origin should be on the surface, maybe halfway between the pins, or at the center of what you might think of as a circular pattern of two pins. Maybe that seems a little abstract, but it doesn't have to be. Datum reference frame M primary, N secondary can absolutely be simulated with a gauge. Actually, it would look a lot like the gauge I showed you a minute ago. We can have virtual condition holes in the gauge and thread locators for the quarter 20 holes. No problem. All right, so let's look at the part on the other side of this interface, which is GD&T Guy 00410. On this one, have a look at the callout for the 2x locating holes here, which I'm calling out as a datum pattern of features, datum B for this part. I have perfect position at maximum material condition, which means that whatever our MMC is, that's also our virtual condition. When I sized these holes, I made sure the MMC, the small size, is more than the virtual condition of the pins on part 409, which was 0.2543 diameter. All right, so these holes start at 0.255, where they would have to have perfect distance between them, and go up to 0.259, where they could have, I guess, 4 thousandths of deviation. This is a tight tolerance, but probably doable, and maybe even preferable to the machinist versus milling a slot. So let's think about worst cases here. If we had the smallest pins and the largest holes, but they were all in exact position and perfectly perpendicular, that would be 259 minus 0.2503, so 8.7 thousandths of allowance. If you were hoping for an allowance of like tenths of a thousandth of an inch, this may sound awful to you, but I would just ask you to consider that for many applications, it might be just fine. 8.7 thousandths may be just barely perceptible. And remember, it's my worst case, just using these numbers. As long as we're entertaining the idea of several thousandths of allowance, let's look at one more part in drawing in this video. This is GD&T Guy 00411. For this one, I don't have dowel pins. Instead, I have just a couple of milled cylindrical bosses that kind of look like pins. So what's not to like about this? Well, I've been saying that these parts are aluminum with steel dowel pins. Aluminum is quite a bit softer than steel, so these would be more likely to wear or become mushroom-headed. And I added some chamfers to combat the mushroom heading. These would also have less shear strength than the steel dowel pins. I'm showing them down here in a pocket, which is something I like for a couple of reasons. One, they don't get sheared off or bent when someone decides to roughly stack these parts. And two, I have material down in this pocket to create the bosses. I don't have to buy a thicker plate of aluminum to make them and then machine 99.9% of it away. And maybe the pocket makes me less concerned about the shear too? So let's take a closer look at this drawing. GD&T Guy 00411. These callouts should be looking familiar by now, I hope. Let's look what I put for those bosses. This is a lot like the call out for the pins in GD&T Guy 00409, only here I give a size tolerance for the bosses, 249 plus 1 minus 2. Referencing datum M primary, I give a perfect position at MMC, so the virtual condition is 250 plus 0, 250. And then for the worst case allowance, these could go down to 247. If we're using GD&T Guy 00410, made it up to this part, I guess we do 259 minus 247, so 12 thousandths max allowance. All right, let's cut it off there for this video, even though I have a few more examples I want to show you. Those are going to have to be in the next one. So please like and subscribe so you're sure to see them when I post it. Until then, this is the GD&T Guy signing out.